So it's great to have you, Alid. If you could introduce yourselves a little bit for our audience.
Yeah, sure. So yeah, my name is Deakin Roberts. My background is chemistry. I did a master's degree in chemistry at the University of Liverpool. Towards the end of my degree, I started to specialise into material science and engineering. And then I did my fourth year project, which was, the interface of materials engineering with some nanomedicine. And then I stayed on with the same research group to do a PhD. That was materials chemistry at the interface of electrochemistry, so making porous materials for lithium-ion battery electrodes. And the main reason I picked that PhD was because I got the opportunity to live and work in Singapore for 2 years. So that was really cool. However, I didn't really like the electrochemistry side of the PhD, but I did like the materials aspect. So after that, I decided to pivot into something else, and I stumbled across a postdoc, which was essentially the interface of materials engineering and biotechnology. Basically, it was collaborating with some synthetic biologists who were producing synthetic spider silk, and they were producing it, passing it over to the materials side of the team, which I joined. And then we were spinning that synthetic spider silk into fibers, to try and make synthetic silk fibers, which should be stronger and tougher than a lot of conventional materials. And I really like that interface. So after that, I did my best to stay at that kind of niche interface. And I got quite lucky. I did a few postdocs, and every time one was coming to an end, another popped up. This was in Manchester, sorry, and other postdocs popped up in Manchester on that interface. So then I went to work for someone else, but it was related, and this was more kind of involved in the synthetic biology. So I started to have to learn the actual kind of synthetic biology techniques myself, which was interesting. I felt like a third year again, just learning like really basic techniques and making lots of silly mistakes in the lab, but luckily I had a really good mentor, and that was again kind of at the interface. We were making these synthetic proteins and then testing them as glues and adhesives, and then from that project we found that basically through a control experiment, a simple protein we were using, it's called bovine serum albumin, was a really good adhesive. In fact, it was supposed to be a control experiment, but it was actually better than most of our actual kind of synthetic proteins. So we're like, well, why are we going to the effort of making all these proteins when we can just use this relatively cheap one we can just buy from a supplier? So we found it was a good adhesive for sticking glass together, especially. So then from there we thought, well, if we can stick two sheets of glass together, it should also be able to stick together sand, because sand and glass are both silicon dioxide, to make maybe like a composite, biocomposite type material. So we did that. Initially it was just a quick kind of scouting experiment, and we found that it worked. And then we thought, this is interesting, where can we go with this? And that's where we looked around a bit and found that it would be interesting to see if it would work with simulated moon dust and Mars dust, because they are also mainly silica based. So if we can stick together sand, it should be able to stick together moon dust, Mars dust, and potentially make a construction material we can use on the moon and Mars. And that's basically how I got onto my current kind of area of biocomposite materials.
Nice. So now you are the CEO of Deakin Biohybrid Materials, is that correct?
Yeah, that's right, Deakin Bio. So actually I've recently passed over the title of CEO to someone a lot more competent. I am not a CEO material, basically. I am a inventor, I'm a CTO. I do science and invent stuff. I am rubbish at the business development side. I just don't know what's going on. So I started this startup over the COVID lockdown. Basically, because I was locked out of the lab, I couldn't really do much. So I thought, I'll just buy some kit in and keep going investigating things I was interested in my cellar, and I kind of went down a path from there. And yeah, developed like some new materials, and I thought, these potentially have, commercial applications. So let's go down a startup route. And so I did that, and yeah, I've just kind of been doing that on the side for about a year now.
So you still do your postdoctoral research alongside that?
Yeah, that's right. So my main job, I'm still fully employed at the University of Manchester as a research scientist, essentially. And the startup is, yeah, something on the side. I do evenings and weekends when I can. Like I said, I've not fully committed to it. I've not taken the plunge. If I was to take the plunge and, raise kind of initial kind of seed funding, I would have to commit to it full time. And it's not, something I've committed to just yet. I've stayed as a full-time researcher as my primary kind of job.
Yeah, fair enough. And does your research sort of overlap with that, or is it separate?
Yes, it overlaps to some degree. So the way it worked was, as I mentioned before, we discovered this BSA protein is quite a good adhesive, and we investigated it to stick together simulated moon dust and Mars dust to make like a biocomposite, bioconcrete type material. And I was really interested in this, but my line manager wanted me mainly to focus on another aspect of work, but let me have enough autonomy to pursue that as out of interest. But didn't really want me to pursue it as kind of like my full kind of like dedicated kind of career path, because it wasn't in alignment with my actual kind of roles and responsibilities in my job.
Right.
And then we were held up by just the publication process for months and months. We sent it off to a journal after we'd finished writing it up, and this was all delayed by COVID as well. So it was really, really stretched out between doing the work and then actually getting it published. And in that time, I went to my boss and was like, I'm still interested in this. Would it be okay if I, carried on working on this concept, in my own time with my own startup? And he was like, yeah, that's fine. And it was also signed off by the university just in case there was kind of conflict of interest issues or IP entitlement issues. And they all said it was fine. But then when the publication came out, it went down really well, and we got a press release out, and it's picked up quite a lot. So then after that, my boss was more keen, and he was like, you know what, you can carry on doing this research, because it's gone down quite well, and it's, because he's more like on the synthetic biology type of things. He doesn't really do too much in materials, so he's kind of just lets me kind of get on with that now. So yeah, now there is a bit of an overlap. I did transfer, so I was working on like a concept with my startup, but I was struggling a bit because I didn't have access to characterization equipment that I would have in the university and stuff like that. And then I decided to transfer some of the stuff I developed as my startup into the university, just because I didn't see too much commercial application for this notion, and it was essentially using starch as a binder. So I moved away from proteins to focusing on starch with my startup. And essentially one of the issues with starch is it has more kind of sensitivity to moisture and water, and we couldn't overcome those issues easily. So it didn't look like it was going to be a viable kind of material for earth-based applications, because if you make a concrete or make a tile, and if it gets a bit wet, it gets damaged or goes soft, it's no good. But there's no significant moisture on the moon and Mars. And that's what the focus in work was in the University of Manchester, was the space applications. So I developed this with my startup, but I was actually, the main kind of Achilles heel of the material doesn't really apply in space, because it's never going to rain on the materials in the moon and Mars, because there's barely any moisture. So I thought, okay, well, I'll just transfer that in, develop it. It's going to be a lot easier because I actually use the proper equipment and use my kind of full kind of research time to focus on it. So there is some overlap in that regard. And initially I was trying to keep them like separate, but now they've overlapped a bit. But I've made them a lot of the process is open source now, so it doesn't really matter, and there's kind of more free flow. And I'm less concerned of kind of IP entitlement issues now, because I've gone down the more kind of open source route as well.
Yeah, nice. So what materials are you actually focusing on at the startup?
So the main materials we're focusing on the startup are tiles. So one of them is called Farbalith or Farvalith, and essentially that is captured carbon dioxide in the form of carbonate minerals. So one of the ways you can capture carbon dioxide is basically take some ashes from anywhere you're burning stuff, and then combine some of the carbon dioxide from the exhaust along with the moisture from the exhaust with the ashes, and then some of that carbon dioxide will react with the metal oxides, the calcium oxide, magnesium oxide, and it will form carbonates. So it's an energetically favorable reaction, so you don't have to put energy in to capture this carbon dioxide. It will happen automatically, and that's great, because other kind of ways to capture carbon dioxide, you have to put a lot of energy in to actually fix it. This just happens automatically. So that's one of the ways you can capture carbon dioxide, and you're left with this just pile of carbonated ashes, which isn't really that much use to anyone. So we really wanted to find like an application for this captured carbon dioxide to utilize it. So, you know, you don't have a pile of useless ashes you have to like pay to bury. You can actually turn it into something useful. So we take this captured carbon dioxide and we combine it with a binder, a protein-based binder that we get from chickpeas. So if you've ever opened a can of chickpeas, drained away that gross water, that is the binder we use. And that is the thing we've made open source, because we thought, but basically you combine it, you mix it, and you compress it, and you can make like a tile-like material. And we thought, this is really good, this is interesting. And ordinary ceramic tiles, because they have to be fired at high temperatures, they have quite a high carbon footprint. So it has a much lower carbon footprint. By our calculations, about 72% less, just from the fact it doesn't have to be fired, because our process, you just have to dry it and then it goes hard. You don't need to fire it at 1,000 degrees Celsius or whatnot. But it's also utilizing carbon dioxide, so that further reduces the carbon footprint. It could potentially make it carbon negative, but I don't like to throw that term around without having it thoroughly evaluated, you know, the whole kind of life cycle analyzed. But yeah, essentially, if it displaces ordinary ceramics, and it's much greener. So that's the main product we're focusing on. And yeah, so we're developing the formulation, the processing to optimize the processes, get it as good as possible in terms of mechanical properties, investigating different things, different additives we can incorporate into it. We're interested in adding graphene to it at the moment. And you can't add graphene to ordinary ceramics, because again, the high temperature oxidative firing, sintering process would burn away anything organic. So we can incorporate graphene into our materials, whereas ordinary ceramics can't, and other kind of organic dyes and stuff. So we're just kind of exploring that experimental space and developing a few kind of technology product concepts, you know, different colors, different styles, different textures, and things like that. So that's the main one we're focusing on. And another one is similar, but it uses.
Sorry to cut you off. Where do you see that being applied?
So essentially, yeah, so as an alternative to ceramic tiles, the main kind of like beachhead market we're targeting is mostly like decorative applications, maybe in like new builds. So if new builds, they have stricter and stricter regulations in terms of carbon footprint, but also the embodied carbon, the materials used to build new buildings, and especially kind of big kind of commercial developments. They'll often, you know, we make or break the carbon footprint. So if an architect says, oh, we're going to use greener materials, we're going to use wood and, you know, these relatively low carbon tiles, you know, for a bid, then they're more likely to get accepted. So I'm thinking that would be a good initial beachhead market, and then it depends on, you know, how much we can produce as to what other kind of future markets we can get into.
Yeah, sounds good. Yeah, sorry, I cut you off. You're about to get onto the second one.
Yeah, and the second one is similar, but it uses algae as a binder. So essentially, it's called the cyanobacteria, but it's basically a photosynthetic bacteria. So it grows and it feeds itself. So it's sort of autotrophic. It feeds itself from sunlight and carbon dioxide.
Right.
And this is of quite a lot of interest in industrial biotechnology at the moment, because if you can grow a bacteria, you don't have to give it sugar. You just give it sunlight, and it will take in carbon dioxide and produce biomass. Then that's fantastic. So we're looking at using the algae as a binder for our materials, and it's looking good so far. Material properties are looking quite nice, and one of the nice things about it is it's really colorful, so you can get like really kind of like intense greens and intense blues.
Nice.
So that's another relatively green tile product we're developing.
And that's using the cyanobacteria instead of starch you were using before to bind things, was it, or the BSA?
Yeah. So we are essentially focusing two classes of binder, protein-based binders and starch-based binders. We really want to move towards plant sources. So initially we're looking at BSA, bovine serum albumin, but that's not sustainable because cows aren't good for the environment. We also looked at things like egg white binders, because they've been used historically to glue things together, but again, because it's coming from an animal, it's not super sustainable. And that's where we kind of shifted to the chickpea juice, chickpea aquafaba, because it's used by vegans as an egg white substitute, and it behaves in a very similar way to egg white. So that's how we discovered that type of protein-based binder. And then starches as well is another class of proteins of quite different to starches in terms of their behavior and structure and all that. But you've managed to make starches work as well. But our process is quite like diverse in terms of we can use like quite different types of starches from lots of different sources, proteins from lots of different sources. And so for the algae, it's kind of a mixture. They're mostly protein, but there is like a mixture of other kind of biopolymers, even like DNA is going to be a significant proportion of the biomass there. But yeah, our process seems to work quite fine with starches, proteins, and other biopolymers.
Okay, yeah. Those animal derived proteins are literally from the animal. I always assumed that someone was just growing a cell and expressing it and purifying it that way. I never realized they were literally coming from the animal.
Yeah, I think the bovine serum albumin, I think it comes, I'm not sure if it comes from the cow blood or like the cow fetus kind of embryonic fluid, is it called? The fetus kind of fluids. Yeah. That's my understanding anyway. I think that's why it's relatively cheap, just because it's kind of like a byproduct from abattoirs.
Right, yeah. And then the cyanobacteria can replace these adhesion molecules?
Yeah. So the BSA was just kind of the initial kind of proof of principle. And then, now we're focusing exclusively on plant-derived proteins and carbohydrates, and in particular from cyanobacteria, just because it's so efficient. Even compared to plants, plants have to put a lot of energy into like growing their stems and developing and producing their starch in their seeds or their roots, whereas cyanobacteria, they just kind of float around happily, absorbing sunlight, producing biomass. So they're very efficient in that regard. Yeah.
And is it so you're producing some proteins with the cyanobacteria, is that correct?
At the moment, it's just the natural proteins.
Okay.
So it's just the natural kind of gunk and proteins that the cyanobacteria produce. But we're absolutely interested in using the tools of synthetic biology to engineer the cyanobacteria to produce stickier proteins, maybe spider silk-based proteins, or kind of like the adhesive kind of proteins that mussels use when they stick onto like slimy rocks in the sea would be quite interesting, because that would be like a waterproof adhesive. So yeah, we're actually interested in going down that path. But at the moment, the natural spirulina from the packet, just bought from Amazon, works well, and that's very cheap. So it's good for our initial kind of, until we get like a lot of funding and where we can sustain kind of synthetic biology activities and serious R&D. We're happy to just use the cheap stuff for now.
Nice. Is it so that the main, I guess, advantage of these materials is the green side of it, or is there material property advantages as well?
Yeah, so the main advantage, as you say, is the kind of green credentials. That's what we're pushing, and that's kind of like the core of all our research and development. So that's why we've moved away. We've barely looked at egg binders, for example, because we know that plant binders are going to be greener. So let's focus on that, and that's why we've moved towards cyanobacteria as well, just because that's going to be super green. But the materials do have interesting material properties in themselves, so that the structure of the materials is similar to natural composites. So if you look at shells or pearl under like an electron microscope and analyze the structure, it's basically lots of small particles of inorganic material. So yeah, pearls and shell are like calcium carbonate, and it's all kind of glued together like a brick and mortar type structure, and the glue is biopolymers, so it's a mixture of proteins and carbohydrates. So essentially what we're doing is mimicking these natural materials, and yeah, the properties of pearl and tooth enamel and shells, they're very strong, especially compared to the constituent kind of inorganic component. Sorry, I forgot what your question was now. Sorry.
The question was, is the main advantage the green advantage, or are there property advantages as well?
Yeah, that was it. Yeah, sorry. Yeah, so they do have interesting material properties as well. So if you look at an ordinary natural shell, it's made of a mineral called aragonite, which is a form of calcium carbonate. But the way the shell is kind of like processes it makes the it's 3,000 times stronger in terms. Its fracture toughness is like 3,000 times greater. So basically, it's resistant to fracturing. Is 3,000 times greater than the natural kind of mineral alone. And we found that our materials have, because they're bio-inspired, they also have some kind of like interesting material properties. So just as an example, one of our latest starch-based biocomposite materials has a compressive strength of 91 megapascals, and ordinary concrete has a strength of up to 41 megapascals typically. So this is like twice as strong as ordinary concrete.
Wow.
And you can get high strength concrete, and that's usually defined as between 42 and 90 megapascals, and we've got ours to 91 megapascals. And obviously concrete's been developed for since the Romans initially invented it, and it's seriously been developed and investigated for 100 years or so. So there's probably a lot more we could unlock if we had like the resources and the time to investigate further. But yeah, they do have really interesting properties, and yeah, we've mostly just scratched the surface really in terms of what we could potentially unlock with them.
Yeah, that sounds incredible. Twice as strong as regular concrete. I'm sure that would go down well if but you said the issue of the starch was it can't really take contact with water, is it?
That's right, yeah. So this material, we call it Starcrete, starch concrete. The main application at the moment is building on the moon and Mars. So if we're going to send astronauts to the moon and Mars, even for not even very long periods, months duration, and a Martian mission is going to have to be, at least a couple of years long, just because the orbits of the moon of the Earth and Mars are going to be, the other side of the sun. And one of the big challenges is radiation. So the Earth is protected by a magnetic field which deflects a lot of radiation from the sun and space. As soon as you get out of low Earth orbit to the moon and to Mars, humans are going to, have quite substantial radiation kind of exposure. So we were going to have to build structures on the moon and Mars to protect inhabitants from radiation. So we need to take the resources we can obtain there, moon dust, Mars dust, and stick it together essentially to make like a construction material. And yeah, so we found that starch can stick this together, and there's no significant moisture, like I said, on the moon and Mars. So the kind of main kind of like Achilles heel of Starcrete doesn't really apply on the moon and Mars. So it's got these really interesting properties, especially the compressive strength is really high. Basically, twice as strong as ordinary concrete within the domain really of high strength concrete. But yeah, as you say, its weakness is moisture. So if we're going to apply it on Earth, there's still some more research and development that needs to be done to overcome those challenges. I'm fairly confident it could be overcome. And again, like, we're very, very small at the moment. We've only just scratched the surface, but we've already got quite a few ideas as to how we could potentially overcome the moisture sensitivity problems and potentially have a much greener alternative to concrete.
Okay, yeah, that's helpful. I think it would be really cool to see this used widespread. I think biomaterials are definitely the future. So you mentioned sort of the space travel, the mission to Mars, let's call it, I guess.
Yeah.
What got you interested in that sort of area? And I feel like it's, I guess, I don't know too many biologists. I suppose you're a material scientist originally, but I don't know too many biologists in that area, so it's quite interesting.
Yeah, so I've always kind of been interested in space, since I was young. But my research had never really touched upon space until we just stumbled upon it. We're literally just kind of looking for potential kind of applications for our biocomposite materials. And I think it was just from a YouTube video I was watching, just out of interest, that I realized actually that material we're developing in work, it could actually, be useful for this. And, again, I think it was like a YouTube video, which kind of informed me that moon dust and Mars dust were like mostly silicon dioxide. And I was like, that's like the same as sand. And we've already shown that sand can work. So that's how I got into space research, space from like a research perspective. And then it just kind of took off, pun intended. I was just interested in it, and when you're interested in something, then it's really easy to, kind of just focus on it, and just motivated to work on it. And it's just been one of those projects that just happens to work. I've been on loads of projects before, and it's just, it just doesn't work, and you spend a lot of time just banging your head against the wall. Was this one just happened to, be quite lucky with it, and made like quite good progress.
Nice. Did you so are there materials in sort of large scale production yet, or is it just lab bench stuff at the moment?
It's just lab scale, really. And by lab, it's mostly my cellar and my living room. I've got a 50-ton hydraulic press in my living room, which my wife isn't too happy about. So yeah, it's quite small scale at the moment. I've tried to apply for various sources of funding to try and expand, but I've not been successful yet. And I've basically concluded that I'm no good at being, kind of like the CEO, the boss of the operation. So I've been able to find someone very capable, Aoife Taylor, to pass the baton on, and I'm just going to focus on doing my crazy experiments, and she's going to be CEO from now on.
Nice, yeah. So you can focus on the science, and she can get you some funding and hopefully do some more R&D with that.
Exactly.
How was it sort of setting up your own lab? That sounds pretty cool.
Yeah, it kind of happened in drips and drabs. So I got really lucky with my first house. So basically, yeah, my wife and I, we got our first house just before the lockdown, and it was in an area which is quite deprived, but it's just on the edge of that area. So our postcode basically is in the deprived area, but we're right next to nicer areas, so we get the niceness of the nice areas, and it's quite a big house for the amount we paid for it. And it included, importantly, a big cellar. And it was like, wow, this cellar's so big, like what are we going to do with it? And then COVID struck a few months later. And there was nothing to do with those initial months of COVID, like barely any work to do. And when you're lab based, there's only so much you can, Zoom meetings you can have, or kind of literature, desk based research you can do. So I started just thinking, oh, I could just quite easily buy in a few bits from eBay, from Amazon, and set up, a bit of a lab from home. And the type of research is really kind of straightforward. You don't need any expensive equipment or fumants or anything. It's a lot of it's just kind of bucket chemistry, mixing things you can buy from Amazon together, and microwaving it and things like that. And then I bought a few bits of equipment. A bit further on, I was very fortunate to get a grant from the University of Manchester for £2,000 from the Masood Entrepreneurship Centre, and that let me buy a 50-ton hydraulic press. And fortunately, it was about 10 times heavier than I was expecting. I bought it from Amazon. I thought, oh, if Amazon ships it, it can't be that big. Yeah. And it was like, even the delivery driver like phoned me up and was like, I think you got the wrong address. It says it's like a residential address. Luckily, he was very helpful, and I managed to find a passing window cleaner who happened to be like a body lifter. So I got really lucky.
Oh, perfect. Yeah.
They helped me get it into the house. And it's way too big to get into the cellar, so it's just been in my living room since then, to the annoyance of my wife. But she's very tolerant, actually, and she's okay with it. So that was the biggest challenge in terms of setting up a lab in my house. Yeah, I was very lucky to have quite a big cellar, so I've got all the basics, weighing scale and cupboards to keep all the various bits and pieces. So yeah, that's basically how it went.
Nice. And you still do work in that?
Yeah. So it's really easy actually to work from home, because you can just pop down and just do one or two things and then go upstairs and have dinner. If I had to go all the way to work just to do one or two random things, then I wouldn't bother. So it makes working in the lab very comfortable and easy. If I'm just on the weekend and like, oh, I might as well just do that experiment I was thinking about. It was only going to take a couple of hours, whereas the effort to actually go all the way to work and do it is a lot harder when you can just do it in your pajamas and dressing gown. Like,
yeah, that's cool. It's like almost I'm not sure about you if you've heard this, but I have a lot of people sort of around me that are talking about trying to get into data science and machine learning, because you have the perks of just being able to work from home. You don't have to go into the lab. Well, you've sort of got that perk, but you also get the fun of working in a lab as well. So
yeah, no, a lot of people who put like a lot of their skill points into computational stuff for that advantage. I'm not naturally good at computers, so I didn't put any skill points into computers. And yeah, I always kind of envied the people who could just work from home and type away and not need to go into the lab. So yeah, I feel really lucky that I've managed to stumble upon a way to work from home that doesn't involve computational stuff.
yeah, it's cool. I think that's most of the actually I did want to touch on the open source
Sure.
I guess idea. Is it? It's not an idea. Open source philosophy. What made you sort of go down that route, and how is that going?
Yeah, I'm glad I went down the route. So basically, I felt like I had this idea, and I felt like it was a good idea. all these materials I was developing, but I just couldn't kind of get it out there and apply it in the real world. So I thought, a better way to do it is to just, give it to the world for free. Let anyone, develop these materials if they think they can actually, develop the business. Because my main kind of motivation is to have like a good impact in the world, develop these green materials to help kind of, reduce carbon dioxide emissions. So I didn't feel like I was a good person to actually, drive a business forward to do that. So the best way to achieve that goal of helping the world was to give the general kind of concepts away for free, but then have my business being, I'm here as a consultant. If anyone wants to seriously develop it, then they can hire me. So since then, like as I mentioned, I found the CEO and we're giving it the commercial kind of startup route another shot. But I'm still very glad I kind of got it off my chest and let the world have like the basic kind of like principles, because I think it is just the right thing to do, and that is like my main motivation.
Yeah, nice. Yeah. All right. It's been a great interview. Thank you very much. I think that's all. Is there anything else you wanted to mention?
No, I think that's it. Thanks very much for having me, Luke. It's been great.
Yeah, my pleasure. Thank you very much.